we'll get started. Okay. So today we'll look at a short module on how to solve linear equations. Okay. This is essentially an extension of how we normally solve a set of linear equations. You know how to solve it, right? We'll just dig a little deeper into it and give it a name. Give that particular method a name. Okay. And the name of the method is called Gaussian elimination. Okay. Okay. We're dealing with a set of equations like this. Okay. M. Oh, here I've written M equations and N unknowns. So yeah, M equations, N unknowns. Okay. So what can we? So we can write it as AX equals B. What do we know about the shapes of these? Yeah, go ahead. Tell me. What is the shape of A? Yep. Shape of A? Okay, all right. Requires more revision. You guys will have to go back. This will be M cross N. This will be N cross 1. And this will be M cross 1. Okay. And Gaussian elimination is essentially a systematic way of simplifying these equations so that the solutions become so that we can easily solve it. Okay. And there are 3 steps involved in Gaussian elimination. Okay. And these are the only 3 steps. Interchange of equations. So you can change equation I. The positions of the equations don't matter. What I'm calling equation 1 could very well be equation 23. Okay. So that does not matter. You can switch the order of in which you write down the equation, and the solutions will remain the same, which is obvious, right? It doesn't matter whether I write the last equation first or the first equation last. The second one, maybe this is not entirely obvious, is if you take an equation and multiply that entire equation by alpha, the solution does not change, which makes sense again, right? And the third one, maybe this is a bit not clear. If you take equation J and if you add a scaled version of another equation to it, where alpha is not 0, okay, that is another operation that is allowed, and this also does not change your solution. Okay. And these are essentially the 3 steps we will do repeatedly to then arrive at a simplified version of the set of equations so that the equations can be very easily solved. Okay. These are operations in terms of equations, right? But we said we are going to represent linear equations in this form, right? So we need to look at what these 3 operations correspond to in terms of manipulating a matrix, the A matrix or AB matrix, in fact. So we have AX equals B. The solution entirely depends on A and B, right? So what we do is what we first make an augmented matrix called A, and then we append the column, another column which is essentially B. What is the shape of this? I've just added one more column. So this will be M, and we call this the augmented matrix. And we essentially, now to solve the system of equations, we will have to use this augmented augmented matrix and just perform row operations on the augmented matrix, because the 3 operations that we perform on the different equations in Gaussian elimination corresponds to operating the rows, because the equations correspond to the rows of the matrix. And when you do this, when you simplify it, we'll see what the simplified version is. What will happen is once you get it to the simplified, uh, it becomes easy to find out the nature of the solution. That means, is it solvable? If it's solvable, does it have a unique solution or infinitely many solutions? That becomes very easily visible. And of course, we can find the solution. Whenever it can be solved, we will find either the unique solution or all the infinite solutions, or at least a way of generating all the infinite solutions. Right? And the procedure is very simple, right? So let's say we are dealing with an equation like this, set of equations like this. This can be written as an augmented matrix of this form, right? Where this is A, this is B. Okay? So in Gaussian elimination, what we do is we take the main diagonal of a matrix, right? We can talk about the main diagonal as elements whose row and column indices are the same. So even if you have a rectangular matrix, you can still talk about the diagonal elements. It's just these are elements where the row index and the column index are the same. So the first row, it will be the element in the first column. For the second row, it will be the second element in the second column, and so on and so forth. Right? What we do in Gaussian elimination is we convert this augmented matrix in such a way that the main diagonal, all the elements below the main diagonal are all made zero by simply following these three rules. Uh, uh, Interchanging equations, that means interchanging rows, scaling an equation, multiplying a row by a scalar, and adding a scaled version of another equation to a equation. That means scaling a row and then adding it to another row. These are the three operations we are allowed to try and make all the elements below the main diagonal zero. Okay, and the main diagonal itself should not be zero. The elements in this main diagonal ideally should not be zero, but we'll see that there are cases where it will be zero, and we'll see how to handle that. Okay, so let's see how to do this, right? So this is our matrix, and here in Gaussian elimination, the terminology used is the diagonal elements are called pivots. Okay, so for example, here this is the first pivot. Okay, and whenever you choose a pivot, what you do is you try and make every element below that pivot zero. You leave the above, whatever is above as it is. You don't touch it. You try and make everything else below zero. Okay, using those three operations. Okay? Now, if you want, so the first thing you check is this. You check if the pivot is zero or non-zero. If it's zero, then you simply swap that equation with something below so that you get a non-zero pivot. So here we start with 1. It's a non-zero pivot, so we don't have to do a row exchange operation. The next thing we do is we try and make the number right below that 0. If it's 0, then you move to the next one. Okay. So to make this element 0, if I subtract equation 2 times the first equation with the second equation, I can make this 0. We're not worried about any other element in that row. We're only interested in the element right below the pivot we are interested in, right? So if you take 2 times the first equation and subtract it from the second equation, what will you get? Of course, this will become 0. 2 times this, 3 minus 2 times this, that will be minus 1. Minus 2 times this, that will be 6. And then minus 2 times the first 2 times this element plus 4, that will give you 2. Okay? Now we made this 0. Right? The next step is now we go below and then try and make this element 0. You simply now take 2 times the first equation, and you always use the equation where your pivot is. You don't use any other equation when you're trying to make everything 0. You take this equation, multiply it by 2, and add it to this, and this will become 0. If you do that, then you end up with this equation or this row. This element will become 0, and coincidentally, this element will also be 0. It might, in general, it won't be, it need not be 0, but in this case, it turns out to be 0, and that's it, right? And then this becomes minus 1. This becomes minus 1 as well, right? Once you're done with this, then you move on to the next pivot. Okay, in the in the revised matrix, in the matrix that you operated on, where you made all the elements below that first pivot 0. So you move to the next pivot, it's non-zero, so you don't have to do a swapping operation. And if you look below, right, everything is already 0, so you don't have any work to do. And you simply jump to the next pivot. That's the last pivot. There is nothing to do. There are no rows below it. That's it. You're done. Right? In fact, in this simple system, just working with the first pivot essentially gave us the final form of the matrix that we want. Okay. What do you notice about the shape of A here? Does this modified A, does it have a special shape? It does. What is it? Yes, that's correct. What is it? Yes, this is upper triangle. And that's essentially what we aim for in Gaussian elimination. We try and convert A into an upper triangular form. It's not always possible, but the best that we can get when there is when there is a unique solution is when you have a square A, then what you're trying to do is convert A into an upper triangular matrix. Okay. So this is upper triangle. Fine. But how do I find the solution? But the final goal is the solution, not to convert A into some special form. It turns out that if once you get A to an upper triangular form, while simultaneously operating on B, whatever operation you did on A, you do the same operation to B, so that you get a modified B. The solution is easy. Right? So essentially, this equation X equals B. After you do Gaussian elimination, you get a matrix like this. Okay. A cap is simply what now? 1, 2, minus 1, 0, minus 1, 6, 0, 0, minus 1, x equals 1, 2, minus 1. Whereas you started with this A and this B, after you do Gaussian elimination, you've got this modified A, this modified B. Now the question is this more easily solvable than the original set of equations that we started with? Yes, why? How would you solve this now? Well, if somebody gave you that equation, forget about Gaussian elimination, right? Forget about the fact that we started with this. If I simply gave you an equation like this, how, and I ask you, can you give me a quick solution? How do you solve it? Sorry? Inner? Hey, inner product. Solving linear equations. See, okay, if it's not clear, if I gave you a and a B like this, can you tell me what the equations are? Tell me the equations corresponding to this. What is the first equation? You'll have to be louder. X1. Yeah. Okay. Second equation. Okay. Now, can you tell me if you can solve it quickly? How? Exactly. Well, you already know the equations are in the form where one of the solutions or one of the components is already known. So once you know x3, you can solve this. Once you know that, then you can solve this. So essentially, this process of starting from the last equation and then substituting for its value and going up is called back substitution. So if you hear this term, then you know what somebody is talking about. Right? So the advantage of Gaussian elimination is it brings us to to this matrix A cap and B cap, from which point on you can easily solve A cap x equals B cap by doing back substitution. And if you do that, what is the solution we get? So x3 will be what? X3 will be 1. X3 is 1. What is this? You can, so if you, I won't do it. If you do it, then this is the solution you get. And you can verify that if you substitute this into the original equation, right, you'll get the same solution. I mean, the left hand side and the right hand side will be the same. Right. So that's basic Gaussian elimination. See. you can continue this simplification process instead of stopping at upper triangular form. Well, you could ask, well, is there another set of row operations I can do where I convert this matrix I got from A to A cap? Is there another set of row operations I can do so that from A cap I get to I? Because once I get into that form, then I have Ix equals some B double cap. The solution is B double cap. So that procedure is called the Gauss-Jordan procedure, where you continue to simplify. Earlier, you made everything below the pivot 0. Now you simply take each pivot and make everything above the pivot 0, starting from the last pivot. Right here. So this is our this is the matrix we got after we did Gaussian elimination. Now you choose the last pivot and make everything above that 0. So if you do that, so you can make, yeah, you take 6 times this equation, add it to this, you get 0. You take okay. I forgot to say one thing, but that you can do later as well. There are two things we need to do: make everything above 0, and we also have to make sure our pivots are all 1 now. So you have to multiply each equation by whatever number you need to multiply it by to make it 1. That's how you will get sorry, where is it? Did I write? So I said we go from A to A cap to I. Yeah. Okay. You can either multiply. You can scale the pivots later or early on. So let's do it further. That's what I've written down here. Okay. So here, from going from this matrix to this matrix, I've done two things. I first look at this pivot. It's not 1. So I do whatever scalar multiplication I need to do to get the pivot to 1. Okay. So to get this to 1, I multiply this equation by -1. So I get this. And once you have it as 1, then you try and make this number 0. If you do that, then you get this row. Okay? And if you continue the same thing above, strange. Okay, you get this, where everything above the last pivot is 0 and the pivot is 1 now. Okay. Once you're done, then you move to the next pivot. Okay. Yeah, I should have written down the steps, but it looks like I multiplied this also by 1. It doesn't matter. You can, so that pivot was originally -1. You multiply that by -1, so you get 1 here. And the first pivot, and then you make this element 0. That gets you, not sure, I need to revise this. I make this 0 as well. And then if I go to this pivot, that's already 1. So my job is done. I don't have to do anything else. Now, once you do all the operations, the Gauss-Jordan operations, to get this to I, whatever is left in the last column, that is the solution. And in fact, the solution was -641. You're essentially just doing back substitution, right? We're just giving it a fancy name. It's just back substitution. Okay. Let's now quickly do this. Let's try and solve this using just Gaussian elimination. Okay. You tell me once you do the steps, what do you get? Maybe I will do it parallelly. So you take 1, 2, -1, 1, 2, 3, 4, 4, -2, -4, 2, -3. What is the first thing you do? Well, you take the first pivot. That's this 1. Okay. Non-zero pivot. Now our next step is try and make everything below that pivot 0. Convert the 2 to 0, convert the -2 to 0. And to do that, we do row operations. So if you take 2 times the first row and subtract it from, or -2 times the first row and add it to the second row, then this element will be 0, right? So tell me what you get for the second row once you do that operation. The first row remains the same. what will be the second row after you do. So the operation we are doing is we are maybe I should write it here. We are taking R2 plus minus 2 times row 2 is converted to row 2 plus minus 2 times row 1. So this will of course be 0. And then tell me what the other elements are. Louder. 1. Are you sure? Hey, it will be 6, no? See, in fact, the 1 is also wrong. You add minus 2 times the first row. So this will be, what is this? 6, 2, 2. 2 times, minus 2 times the first row added to the second row. 4 plus 4 minus 2, which is 2. Okay, all right. We leave the third row as it is. Now we need to make, so the pivot is still this. We need to make the last element 0. Okay, what do you do in that case? What is the operation that we need to do? So here, so we need to modify row 3. So this will be R3 plus 2 times R1. Okay. The first two rows remain the same. 1, 2, minus 1, 1, 0, minus 1, 6, 2. This will be 0. What about the other three elements? Yeah, if you have it, say it out loud so that we don't waste time. Yeah. 0. 0 is it? Okay. Minus 1. Okay. Okay. So that's done. Now, from here, we move on to the next pivot. In fact, if we go to the next pivot, right, it's non-zero. Everything below that is 0. No problem. We're done. Go to the last one. It's a 0 pivot. That's the problem. Okay. The pivot should not be 0 if you want to be able to solve. Okay. We will leave it as it is for now. Okay. Let's do the other one. Here. Let's do the same procedure. 1, 2, minus 1, 1, 2, 3, 4, 4, minus 2, minus 4, 2, minus 2. Let's do this. Let's try and do the same set of procedures. And in fact, you actually don't have to do any of this because if these two are exactly the same. Okay, so this part of the matrix will actually remain the same. You'll simply have to do the operations again for the last column. Yeah, and do that and tell me. So we will again do R2 minus 2 times R1. I know I will get 1, 2, minus 1, 1, 0, minus 1, 6, 2, minus, not 2, sorry. That's wrong. You'll have to check what you will get. Is it, it'll be 2 because this is the same. 4 is the same in both cases. 2. And the last row, of course, remains the same because we've not done anything to it. And then now if you operate on the last row, you'll do R3 plus 2 times R1. If you do that, the first row remains the same. Second row remains the same. What will happen to the third row? I know these three will be 0. What about the last one? Sorry, this is not 3. Minus 2. I'm wrong. This is minus 2. Earlier, when we did x equals b, this part had all non-zero pivots, and it came out nicely. And we were able to do back substitution and solve it. No non-zero pivots. But in these two cases, we are encountering two situations. In the first case, you have a zero pivot. In both these cases, you have a zero pivot. But there is a difference in the last column. In the second equation, right? For the set of rows that have zero pivots, the B augmented column is also 0. This is a situation where you have whereas here the rows of A cap are 0, but B cap is not 0. There is no solution to something like that. You're saying 0 times x1 plus 0 times x2 plus 0 times xn equals 5. There is no solution. There are no numbers x1 to xn that you can choose that will satisfy this. That means this is an example where you have. So this is essentially to demonstrate that if you do Gaussian elimination, it will show you the nature of the solution that you have for for the system of equations that you have. The basic version that you usually do for when you have square matrices. When you have rectangular matrices, then we essentially follow the same procedure, but we do slightly different so that we can figure out the nature of the solution and be able to solve the system of equations to be able to also generate all the possible infinite solutions if it's a system of equations with infinitely many solutions. And the way we do that is very simple. It's just that we will skip one operation that we used to do earlier. Whenever you had a zero pivot, you switch the rows. We don't do that anymore. Okay. Now let's assume that we have an augmented matrix like this. Okay? What is the shape of A? How many equations and how many unknowns do we have if this is the augmented matrix? How many equations? Yeah, louder. 3 equations. How many unknowns? Yeah, 5 unknowns, right? There are 5 columns, 5 unknowns. So this is an equation of 5 unknowns and 3 equations. What does that usually tell you? No. If you have more equations and more unknowns, is it? Not always. If it has a solution, it will have infinitely many. It's possible it's not solvable. But if it has a solution, then for sure it'll have infinitely many solutions. Okay. Now we do the same procedure. We start with the first pivot is not 0. We try and make everything below that 0, right? If you do that, you get to this matrix. When you make everything below the first pivot 0, it turns out everything below the second pivot has also become 0. Okay. So now, according to our Gaussian elimination procedure, you move here, right? It's 0. If this was actually, I should correct myself. You still do row exchange. I'm sorry, there is a mistake. You see if this is 0. If it's 0, you look at everything below. If there is a non-zero row, you switch. And then you try, after you switch, you try and make everything below that 0. But here that is not possible. Everything below that pivot is 0. If that is the case, you simply then move horizontally. You don't move diagonally down, you move horizontally to the next column that has a non-zero pivot. Okay? So now this is 0 and everything below that is 0. So we skip this and then move horizontally. And now we choose this as the pivot. Okay? This was the first pivot and now this is the second pivot. Now with this, we try and make everything below that 0. So if you do that, you get to this. You get to this form. And then we move to the next pivot. So we essentially now have and that's it. There are no equations below this, and you stop there. Now, this is your when you do that, right? You get a matrix of this form. Earlier, if you remember, when you had your augmented matrix, the last column was B, and when you do Gaussian elimination, in the case of a square matrix, right, you had something like this. Right? You had an upper triangular matrix. Right? When you do this operation on a rectangular system of equations, then you essentially have something like this. So you won't have a clean set of diagonals. What you might end up with is something like this. Okay? Everything below these staggered lines or these step lines are 0. Everything above, things above can be non-zero. Okay? And whenever we have a rectangular system of equations and we get it to this form, this is called the row echelon form. Okay? In fact, if in Python or MATLAB, you can actually give a matrix and ask MATLAB to return the row echelon form, and it'll essentially give you this after doing Gaussian elimination. Okay? And the row echelon form has some specific has a specific pattern, right? So if you have this matrix, then you get something like this. Row echelon form, right? So whenever you have a 0 row in the row echelon form, then all the rows below that 0 row will be 0 in the row echelon form. Okay? That's because whenever you see a 0 row, you essentially switch with something that's non-zero. So all the 0 rows get pushed to the bottom. And the first non-zero entry in the ith row, let's say it occurs at the jth position, for example, here. So in the first row, the first non-zero entry occurs in the first column. In the second row, the first non-zero entry occurs at the third column, right? In the row echelon form, whenever you see the first non-zero element, all the elements below that column will be 0. Those are the two defining structures of your row echelon matrix in the row echelon form. And the nice thing about the row echelon form, is it turns out that you can immediately find out the rank of the matrix from once you have the row echelon form. Okay, and the rank of the matrix is essentially the number of pivots that you have. Okay? And the columns that contain the pivots, for example, this, these are the columns that contain the pivots, right? Those are called the basic columns, and the others are non-basic. Once you get into the row echelon form, the rank of the matrix is simply the number of basic columns in the row echelon form form of the matrix. Okay, now you have a practical way of finding out the rank of a matrix. What is the definition of the rank of a matrix? Use the sheet. That's why I gave the sheet. Yes. Yes. The number of linearly independent columns or rows that you can choose from the matrix, or maximum number of linearly independent columns. Right? We can do something similar to what we did with the Gauss-Jordan form earlier, where we did not stop by making the matrix upper triangular. We tried to make the matrix identity. Right? We can do the same thing with the row echelon form as well. You go to each basic column, convert the pivots to 1, and make all the elements above the pivots in the basic column 0 as well. Right? So if you have this form, which is the row echelon form, you try and convert it to this form by doing Gauss-Jordan, and this is called the reduced row echelon form. Okay. Once you do this, what will happen is all your basic columns will be your unit vectors here. Unit vectors from Rm here, because if this is a n cross m matrix, or because we've assumed n cross n matrix, the basic columns will be unit vectors from Rm. What are unit vectors? One element is 1, everything else is non-zero. Okay. So this is E1. The second basic column is E2, E3, E4, E5 from R6. Okay. Now, in the matrix that we saw earlier, this one, let's try and get this to the reduced row echelon form. Okay. So we started with this. That is the row echelon form. Well, I've done it in a different order here, but you choose the last pivot, convert this to 1. So you multiply this by -1, and then make everything above that 0. And then after you do that, you go here, you multiply this by -1, make everything above that 0. And here it's already 1, so you don't have to do anything. Once you do that, you get it to this form. Right? The basic columns are all unit vectors. And this is for the matrix A that we saw earlier, this is the reduced row echelon form. Okay? And the reduced row echelon form is actually quite nice. Okay. So where are the basic columns here? What are the basic columns? Can you tell me the column numbers for the basic columns for this matrix? 1, 3, 4. What are the non-basic? These are basic. Non-basic? Now, if you see this, right, take a non-basic column. Right? It should be clear that the second non-basic column is essentially a linear combination of the first column. It's -2 times the first column. Okay. Now, if you go to the next basic column, 5, can I say the same thing? Can I say it's the linear combination of the columns before it, or at least the basic columns before that column? Yeah. What linear combination would produce the fifth column in terms of the basic columns? Yes. Not minus. No. Why minus? So it's 2 times the first basic column minus 1 times the second basic column, 5 times the third basic column. Yes. Yes. Right. So that's essentially what the reduced row echelon form reveals. It tells you that the second, so the non-basic columns are linear combinations of the basic columns. And whenever you have a non-basic column, right, what does it tell you about the rank of the matrix? Can the rank of the matrix be equal to the number of columns? No. Forget. The matrix A has n columns. If there is a non-basic column, Because there is one column which is a linear combination of the other columns, that means the rank cannot be n, it has to be lesser. Right? Or another way to say that is the rank is simply the number of columns minus the number of non-basic columns, which is essentially the number of basic columns. In fact, the even more incredible thing is that is not true, not just for the reduced row echelon form. If you go to the original matrix, right? So here, the second or the second column is minus 2 times column 1. Column 5 is 2 times column 1 minus 1 times column 3 plus, right? Just remember this. Okay, our original matrix was this. The second column is 2 times the first column. Okay? And you can figure out. So the last fifth column is 2 times minus 1 times the second basic column plus, what will this give me? 2 minus 2 is not what? No, 2 minus 1 0. That's 1. 4 minus 1 3. 3 minus 5. What did I do? Minus 2. Yes, that's correct. Minus 2 minus 3 plus 5. This. Yeah. So essentially, when you do the row echelon form, it reveals the structure of the columns, right? Which I think is quite beautiful. See, one advantage could be, for example, let's say you have very tall matrix for some reason, okay, and let's say this is some 100 times 1 million for some reason. Let's say we have matrix like this. That means you need 10 power 8 floats. You need to store 10 power 8 real numbers or floats, right? Which is maybe small by today's standards, but still it's a big number. Okay. But if you know that there are only 3 basic columns in this matrix, right? Do you have to store all 10 power 8 elements? So here, if I have 100 cross 10 power 6 cross 10 power 2 matrix, I have a matrix that is 10 power 6, 10 power 2. It's got a million rows and 100 columns. Okay. I do the reduced row echelon form and I find that the rank of the matrix is 3. Okay. Now I ask you, okay, if I have to store this matrix, right? Ideally, I should be storing all 10 power 8 elements, million columns, 100 rows. If I know the rank of the matrix is 3, is there a more efficient way I can store this matrix? Yes, exactly. Okay, what would you have to store? 10 power 8 is the total number of, that is the total number of numbers in this array of, in this matrix. What are all the things I have to store for sure? Let's start there. Do I have to store the basic columns? Of course, I have to store the original basic columns, not the reduced row echelon form. You have to store the 3 basic columns. Let's say C1, C59, and C81. These I have to store. These I cannot get away with because they contain information. They contain information that is not contained in anything else. All right. What else do I have to store? Exactly. Here, tell me what all I'll have to. Let's make it simple, right? Let's go to this form. This is a huge matrix. For some reason, we cannot store 15 numbers. Okay? Oh, in fact, this is a bad example. It applies only for tall matrices. So let's stick to this. Let me say you have 5 columns and 10 rows. Let's say there is only one basic column. This is C1. What all will you have to store? How many numbers will you eventually have to store? You'll have to store C1. What else would you have to store? Not solution. There is no solution. We're not trying to solve anything here. We're just trying to see if I know the reduced relation on, if I know the structure of the matrix, can I save it in a better, more efficiently? Okay. In the reduced row echelon form, what can you say about a non-basic column? But it's more specific. It's not just a linear combination. It's only a linear combination of all the basic columns that occurred before it. If that is the case, right here, each of the 4 non-basic columns are only a linear combination of that first column. Because there is only one column, for each of these columns, I only have to store one number. Right? How many times the first basic column is the second column? How many times the first basic column is the third column? So here, essentially, I have to store C1, and then I have to store a single number for each of the 4 columns here. So C1, that is what, 10 numbers. I can actually store this with, instead of storing 50, I could have stored this matrix with just 15 number or 14 numbers. Okay, right. What if C1 and C3 were basic columns? How many numbers would I have? What all would I have to store now? C1, C3 for sure. What else would I have to store? How can I reconstruct the second column? How many numbers would I have to store for reconstructing the second column? Second column. Yes. No. C1, C2. These are the basic columns. Any non-basic column only depends on all the basic columns that occurred before. So until I reach the second basic column, all the columns will only depend on the first column, first basic column. That means I only have to store one number for each of those columns, right? So for the second column, I have to store one number. Third column, I anyway have to store, right? So I skip that. What about the fourth column? How many numbers would I have to store for the fourth column that occurs here? For the fourth and the fifth column? 2. So I'll have to store 2. So essentially now I'll have to store 10 plus. First column, I'll have to store 10 numbers. Second column, I'll have to store one number. Third column, 10 plus 2 plus 2. What if all my columns are basic columns? How many would I have to store then? Yeah, you have to store everything, right? So here you can similarly work out. If the rank is only 3, it will be nice if the basic columns actually are well separated. If the basic columns occur as first 3, you of course have to store 3 million numbers, and then 3 numbers for all the other 97 columns, because all those columns can be a linear, might contain non-zero linear combinations of the 3 basic columns. Okay, that's the idea, right? So that could be one use of finding out the structure in the matrix. Right? Okay, now once we get into that form, then the question is, okay, can we now, how do we use it to find out if there is a unique solution, if there is no solution, or get all the infinite solution, or at least an expression for me to generate all the possible solutions. Okay. So before we do that, we take up this problem. We try and solve the homogeneous solution, because we know that any solution to x equals b, x is what? X contains 2 components. So if I can find all the possible homogeneous solutions, then I can add that to any particular solution. Then I will be able to generate all the infinitely many solutions. So to do that, let's say we try and solve the homogeneous solution. Okay, so we start with the previous example we had. And we got it to, well, this is the row echelon form. When you did the reduced row echelon form, we got it to this. This is the reduced row echelon form. We did this for some ax equals b, but now we want to do ax equals 0. Now the question is, would you have to redo the whole operation again? Actually, you don't have to do anything, because these are 0. No matter what row operations you do, they will all remain 0. So essentially, you only need this. This you don't have to repeat for different b's. Once you've operated on A, you can just keep that reduced row echelon form of A. You might have to redo the same thing if you have different B's. But if the B is 0, then you don't have to do anything. So if you have this, the reduced row echelon form is essentially this. Okay, the last column always remains 0. Right? And once you have it like this, so let's say I call it A cap. We have A cap x equals 0. You can write down the equations now corresponding to this reduced row echelon form. And if you do that, these are the equations you get. X1 minus x2 plus x5 will be 0. That's this. Second equation will be x3 minus x5 will be 0. And the last equation will be x4 plus x5 will be 0. Okay. This means, now let's, and what we do once we have this, right? You choose the elements corresponding to the basic columns. You keep them on the left-hand side and move everything from the elements in X corresponding to the non-basic columns to the right. Okay, that's what we've done here. So X1 is the element of the solution that corresponds to the first basic column. So we keep it on the left and then express that in terms of the non-basic columns. So you're essentially expressing the elements in the basic column in terms of elements in the non-basic column. So x1 will be 2 times x3 minus 2 times x5. x3 will be x5, x4 will be minus x5. That means if I know this, right, or if I know the values for the components corresponding to the non-basic columns, I can find out the values corresponding to the basic columns. That's what this means. Assume the right-hand side, if known, you know the left-hand side. That's how you interpret this. If that is the case, then I can write the general solution like this, right? If I know x2 and x5, right, I can find out x1, x2, and x1, x3, and x4 using this equation. That means I can write it like this: x1 is 2 times x2 minus 2 times x5. x2 will be x2 because x2 is some value that I know or I choose. x3 will be x5. x4 will be, well, this is wrong, minus x5, and x5 will be x5. That means I can write, if you look at this, right, this can be written as a linear combination of two columns scaled by x2 and x5. Okay? This column can be written like this. You can verify this later. So what this means is your homogeneous solution now can be written as a linear combination of two columns. Okay, x2 times this column, x5 times this column. You don't have to call them x2, x5. You can call them alpha, beta. You can choose any real numbers for these. So the set of all possible homogeneous solutions now is alpha times 2, 1, 0, 0, 0 plus beta times minus 2, 0, 1 minus 5, 1. And these two columns, we obtain them essentially by doing the reduced row echelon form for solving x equals 0. And this is in fact the set of all homogeneous solutions for this particular A. Okay, the homogeneous solutions only depend on A. They're independent of B because B is set to 0. Okay, so this is the general form of the solution for for this particular system. So in general, if you have a matrix A, you can take this augmented matrix, do the reduced row echelon form, find the rank. Let's say the rank is R, which is less than n. Well, A is assumed to be m cross n. Okay. The homogeneous solution in general will look like this. It will be a linear combination of a bunch of columns, and the number of columns you will have will be number of columns of the matrix minus the rank. Okay. If all the columns are linearly independent, that means the rank is equal to the number of columns, the homogeneous solution is 0. Because there are no non-basic columns. For example, here you will have no non-basic columns. That means essentially you will have x1 equals 0, x2 equals 0, x3 equals 0, x4 equals 0, x5 equals 0 if this was if this had full rank, right? And each of those columns will be scaled by some alpha 1, alpha 2, alpha 3, so on and so forth. So if we take the linear combinations of these n minus r columns, and remember each of these columns, what space is it from? Rm or Rn, given that A is Rn. This is in the solution space. Okay. And these terms here or the components of your solution X corresponding to the non-basic columns are called the free variables. That means you can freely choose them. Once you freely choose them, the remaining variables are determined by these free variables. Like here. Here we were able to freely choose X2 and X5. X1, X3, and X4 were determined by X2 and X5. The same thing here. Here N was 5, R was 3. So you had, how many columns did you have? 2 columns for generating your homogeneous solutions, and you had 2 free variables, x2 and x5. Yeah, and so here I'm essentially asking, well, what if the rank is n? If the rank is n, then it essentially means that you have no non-basic columns. That is for the homogeneous one. Now the question is, how do you do if you have a non-homogeneous system of equations? The original system of equations we started with. Okay. If you go back a few slides, you'll see that this is what we got it to after you did the reduced row echelon form, and you can now write this as a cap x equals b cap. If you do that, you'll get this, right? X1 minus 2x2 plus 2 times x5 will be equals to 1. X5 minus x5 will be x3 minus x5 will be 0. X4 plus 5 times x5 will be 0. If you now again do the same thing, choose the components corresponding to the non-basic columns as the free variables and move them to the right-hand side, keeping only the components corresponding to the basic columns on the left-hand side. If you do that, then you get an expression like this. Well, this part of the expression, right, is the same as when we did ax equals 0. Okay? What you now have is this some dangling 1. So if you express the solution, right, based on these equations, x2 will be x2 because that's a free variable we choose. X5 will be x5, free variable. X1 will be now 1 plus 2 times x2 minus 2 times x5. X3 will be x5. X4 will be, well, I'm still missing one. Minus x3. Sorry, minus x5. That means I can write it like this. I can write it as some fixed column plus the linear combination of 2 other columns. What do you think this is? We know that this is your particular solution. Okay. Now, if you choose any values for x2 and x5 and you substitute it in the original system of equations, you will be able to solve it. Okay. That is the example where you have a solution and we've figured out how to find out all the possible solutions if there is a solution. But there are situations where you might not have a solution, right? That would happen when you have this. So let's say we started with an augmented matrix like this. You do the reduced row echelon form. Whenever you find a situation like this, where the rows corresponding to the A matrix are all 0, but the corresponding element in the last column is non-zero. Whenever you have a situation like that, then you have a system of equations that cannot be solved. However, if you have a situation where the 0 rows of the A part of the matrix also has zeros in the B part of the augmented reduced row echelon form matrix, that is solvable. It's just that it'll have infinitely many solutions. Or it can have infinitely many solutions. Let me put it that way. But the moment you see this, you cannot solve it. End of story. Okay. And you will have a unique solution whenever, well, going back to those conditions we had, when the number of basic columns equals m number of rows, then you always have am I correct? No, sorry. I'm doing a mistake. No, sorry. I need to think about this. Whenever you have yeah, this is what I should say. The number of basic columns equals number of columns, not rows. Number of columns, then you have unique solution. When it's less than the number of columns, then for sure you have, because if you have less than the number of columns, then you have non-basic columns. Or another way to say this is, now when you take the augmented matrix and you do the reduced row echelon form, get this. Okay. If in this reduced row echelon form, if the last column turns out to be a basic column, okay, then you have a situation where you cannot solve system of equation. Because if you see this, right, this has got a non-zero pivot. Everything else here was 0. So this is all 0. Yes. Then if you come here, you have a non-zero value here. So whenever you have the last column as a, in the augmented matrix, if the last column is a non-basic, if it's a basic column, then the system of equations is not solvable. Okay, that's essentially what this means. If the rank of A is equal to the rank of AB, then the system is solvable. Whenever the rank of AB is greater than the rank of A, then you have a situation where it cannot be solved. All right, we'll stop here, and then next class we'll look at the first of the several matrix factorization methods that we'll see, which is essentially comes from Gaussian elimination. Okay? All right, that's all. So for the midterm, you will have this part as well, Gaussian elimination, because it's essentially solving linear equation. So I would prepare for this as well.